All right, this is the second part of color perception.
So I'm going to start this second part of color perception by just finishing up what we were doing last time, the very last slide that we didn't have time for, asking which of those color vision theories is correct. And I hope that throughout all of that it became clear that both of them were correct, that trichromatic theory of color vision tells us what is happening at that earlier level of processing at the point of the photoreceptors, so that we have those three kinds of cones, those three color mechanisms in the retina that are going to be responding differently to different wavelength information. And then opponent processes occur at later levels of processing because of the integration of the inhibitory and excitatory signals. So yes, again, we end up in the retinal ganglion cells and the lateral geniculate nucleus cells with a center surround receptive fields, and we have this red-green on-off and blue-yellow kind of on-off, off-on, both inhibitory, excitatory, and vice versa, going both directions. That's happening because of that integration that we saw from the photoreceptors to the retinal ganglion cells. And we do also have neurons that respond have these kind of opponent responses at the level of the cortex as well, which we'll talk about again later. And here's my slide. So with the short, medium, and long wavelength cones, the absorption spectra, really like the relative proportion of light that they are absorbing. They have these kind of normal curves where there's a maximal kind of place. They're not exactly normal. You can see they're a little bit skewed, but there's a place of maximal absorption. And then the rods also have their maximal level of absorption very close to 500 nanometers. But then those three cones give us our three color mechanisms. And I usually just put this slide up a few times throughout my talks to when I'm teaching face-to-face to remind me to ask for questions. So you might want to pause this and just see, and to allow you to put together a lot of this information, because color vision is kind of complicated in its own way. So if you want to pause and just kind of put things together, this is a good place.
Additional concepts that I need to distinguish are subtractive color mixing and additive color mixing. And I'm going to tell you right now that the first time I taught this material, I was teaching the introductory psychology class at Midlands Technical College, and they got angry with me, and they told me that I was calling their kindergarten teacher a liar, and that's simply not true. Kindergarten teachers and elementary school teachers are not going to talk about these scientific words, and the idea with mixing colors is that we're adding colors together. But when we're talking scientifically, what's being subtracted or added in these labels is wavelength information, or what wavelengths are being reflected. And when we are mixing together paints and crayons and things like that, we are continuing. Those colors are absorbing some wavelengths and reflecting some wavelengths. And as we're mixing them, those colors continue to absorb the wavelengths that they were already absorbing. I mix another color, it's still absorbing the wavelengths that it was absorbing. And so we're subtracting out wavelength values, wavelengths that are not being reflected now. And I'm going to do this with a picture that I think makes a lot more sense. So if we look at our different potential paints or pigments here, if we're looking at blue paint, it is going to be reflecting, right, the shorter wavelengths, maybe a little bit of the medium wavelengths. It's going to be absorbing the longer wavelengths. And if we look at yellow paint, blue and yellow are the easiest to look at. If we look at yellow paint, if you remember that, it's going across those medium and long wavelengths of what's being reflected. So it's really reflecting the long wavelengths, and it's also reflecting the medium wavelengths. It's absorbing those shorter wavelengths and not reflecting those. And so if we mix those together, my blue paint continues to absorb the long wavelengths. my yellow paint continues to absorb the short wavelengths, and we're subtracting out those wavelengths from being reflected. And so the only thing being reflected now are the medium wavelengths that both of those paints were reflecting before. So the only thing being reflected is what's common. Everything else that was being absorbed is subtracted out from what's being reflected. When we talk about additive color mixing, again, we're talking about the wavelengths that are being reflected. And so the easiest way to look at it is with theater lights. I'm going to look at a picture in a second that hopefully helps. But if we overlay theater lights, then everything that I'm reflecting with one light, I overlap that some with another light, that everything that it's reflecting, we both continue to reflect everything we were reflecting before. So we're adding together the wavelengths that are reflected. And in additive color mixing, complementary colors mix to an achromatic color. And I'm going to use blue and yellow again, as those are complementary colors. And I've also had students complain about the word complementary. Again, this is not about what the words that we would use in art. These are the words that we're going to use in science. And when we're saying they're complementary, we're going to continue to talk about these colors and what that means. But blue and yellow are complementary colors. And so if I take a yellow light with everything it's reflecting and I overlay it with a blue light and everything it's reflecting, I'm going to see a white light as we get to the achromatic color. Again, this is theater lights, and that's actually occurring out in the world. But if we look at something like the way old TVs work and the way they have these little dots, that if you look really close at the TV at a particular point in the TV, it's going to look like little dots. Pointillism, that kind of art, uses the same kind of additive color mixing, where the mix is in the mind. The mix is happening as it's going through neural processing, really. And tapestries do this same kind of thing. And I'm going to show first an example to discuss this with theater lights, and then I'm going to show some examples from pointillism, because that's the best easiest thing to talk about from slides. So if I look at my theater lights and what they are reflecting, and we're going to go back to the blue and yellow, which we just saw with the paints, and I might say that the blue is reflecting short wavelengths. I might say short and a little bit of medium, but whichever. It doesn't really matter where exactly that is. But my blue is down at the short wavelengths end of the spectrum. My yellow light is reflecting medium and long wavelengths. And so when I overlay those, I add to the wavelengths that are being reflected from both of those. So now short, medium, and long wavelengths are being reflected. And that's, again, going that across the electromagnetic spectrum in these complementary colors, and now I get to an achromatic color, which is white light. When we look at pointillism, the mix is in the mind. I took these slides, some of these pictures, from Dr. Robin Morris. One of my students looked up this picture. I've never figured out the artist, and when he looked it up, it looked like it was actually a picture that was not a pointillist painting, but was manipulated with technology to create this. But so what we're seeing here, it looks like a very pale-faced Japanese woman. We're going to see how this is created with tiny dots, and that we are putting that information together to create this perceptual experience. And I never know exactly how this is going to work, but usually on the screen, it's really easy to tell, and I can see it on my laptop, and I hope that you can make this full screen and see that. So what we're seeing is a pale-faced Japanese woman in the previous picture, and you'll have to move back the video because I usually go back and forth a bit here. But she is made up of, you can see some of these really quite dark purple dots on her face. But when we move away from it, we don't see the little dots that are making up her face. It gets mixed in the mind to create a coherent perception of the lighter color, and it's really we're adding together those wavelengths that are the little dots. So another example of a pointillist painting that I had to include, because this one I know, and I know that it's gorgeous. This is a Sunday afternoon on the island of La Grande Jatte. It was created somewhere between 1884 and 86, and this is a painting by Georges Seurat. If you've seen Ferris Bueller's Day Off, you'll see this painting in a movie where they move up close to it. But if you get to go ever to the Art Institute in Chicago, this is a gorgeous painting to see, and it's really quite moving. This is huge. It would probably take up one of my entire walls, and it is created of little dots. And so what I'm showing here, you cannot tell that at all because it's so tiny. But even in the movie, they move up close to it where you can see there's a boy crying a little bit farther back on the left, behind those people with their dog that are kind of in the front, and or his mouth is open. It looks like he's crying, and they close in on that face, and it's just made up of all these little dots. And if you think about him creating this huge painting of all those little dots, it must have taken forever. And it's a beautiful, very moving kind of painting. But again, when you move off from it, you can't tell that at all. The mix is in the mind, and there are lighter colors. It appears lighter than if you're right up on top of the painting. You'll see these darker dots. And again, this is like the way television works. This is the way a lot of tapestries work. So if you get to go to a place where you can move off and away from a tapestry and then move toward it, you'll see it really changes and its depth and appearance and its darkness as you move in towards it. Okay, and so for this to work very well at all, you really do need to pause this here. You have plenty of time. I've been ending these with about 55 minutes to an hour, really. So for an hour and 15-minute class, you can pause this for a moment. If you don't have food coloring at your house, that might be something you decide to put on your grocery list next time you go to the store so that you can do this. And I'm sorry, this is something we usually do in class. It's fun. It's different than just sitting there, and it does go through these concepts. And so if you're mixing the food coloring in some water, do that. Think about that for a second. And I usually ask the questions. So is this selective reflectance or selective transmission? And so remember, we're looking through the water. Usually we've gone over these concepts a class period or two before we look at the food coloring, and so we come back to these concepts. But remember, we're looking through a liquid when we're talking about the water, and so that is selective transmission, right? Those are the wavelengths that are passing through. And then I ask, is this subtractive color mixing or is this additive color mixing? You want to think that through for a moment of what you think. Usually people say additive color mixing because we think of just mixing colors together as adding colors. But remember, when I'm doing additive color mixing, things are going to get lighter and lighter because I'm continuing to add to the wavelengths that are being reflected so that we are perceptually experiencing. Subtractive color mixing, things are going to get darker because we're going to continue to subtract out everything that's being absorbed by each of those colors. And so if you look at what happens and then you add, usually what get a lot of people end out with this icky brown color water. Not everybody, but a lot of people have orange or blue or like a light green, but mostly they get that from just using one or two drops of a single color, or just a little tiny bit of red, like a drop of red and then a little bit of yellow. But a lot of people end out with this dark brown, and there's nothing, they'll start adding yellow to try and make it lighter, but there's nothing you can do to make it lighter because every time you add more color of the colors, you're subtracting out more of the wavelengths. So it just gets darker and darker, and they end up with these brownie kind of things. So this is clearly selective transmission and subtractive color mixing. And again, I'm going to suggest that you go do that exercise on your own somehow. Mix, and if you don't have food coloring and water and you have anything, if you have paint or anything in your house where you can look at this and ask yourself these questions, they're not going to have the same answers, but almost always what we're doing is subtractive color mixing. When we think of mixing colors, it really is in pointillism, TV, tapestries, and if we're using theater lights, those are the examples of additive color mixing. So I hope all that makes sense at this point. I'm going to do a little history here of how we know that white light is made up of the spectral colors of those various wavelengths that are giving us the perception of different colors. This all was originally discovered and discussed by Sir Isaac Newton in about 1704. He came out with his book Optics, where he first makes that distinction between the psychological experience of light, or what we experience as color, and the physical characteristics of light, where he realized that color is not a property of the wavelength itself. It's the brain's way of informing us which wavelengths are present in our environment. And if you want a funny kind of, when you realize that your idols were really wrong about something, you can read about the color war, quote, the color war between Sir Isaac Newton and Goethe, where Goethe I respect a great deal, but he did not believe Sir Isaac Newton and complains a lot about this whole idea that white light is made up of these various colors. And so if we look at a prism, we are taking sunlight through the prism, we are going to see that rainbow of colors, the Roy G. Biv, and they will be those sinusoidal waveforms. And how did Newton actually gain evidence of this? Well, he performed this experiment where he allowed white light to come in through, so I have this card-looking thing here with a circle through it, and so that's a circle that's been taken out, and so the white light is coming through just one little area and going into a prism, and we're seeing the rainbow. Well, he took another bunch of cards, or this gives us the a longer ruler looking, but so something where he could punch out holes, but these were little cards, and he moved those along from the red light to the yellow light to the blue and indigo violet, to those lights that those colors that you could see in the prism. And then he allowed just that light to come through after going through the first prism, and then he put that through a second prism. And what you can kind of tell there, I hope, is kind of clear in the picture, that the longer wavelength light is not being refracted or bent quite as much as the medium, the yellow, or the short, which is being bent the most. So this was showing him that these wavelengths had different physical properties. And so again, our psychological experience of color is telling us what wavelengths are out there. And those wavelengths have different physical properties. They have different wavelengths. And we have now, I have that at the bottom of the color spectrum, going from about 400, those short wavelengths, about 400 nanometers, to those longer wavelengths of about 700 nanometers. And you can see the different properties by looking at that second set of prisms.